Hey guys, let's jump into 4.4. We go. So we're going a little bit out of order here from the textbook. I find L'Hopital's rule fits much better here, and even right after 3.7. L'Hopital's rule is, you could argue, it is an application of rate of change as well, although different from the ones we saw in 3.7. Okay, what's this all about? L'Hopital, okay, French guy. That's how you pronounce his name, phonetically L'Hopital. His rule is a way to find limits that were not possible to do before, back when we were doing limits in chapter 2. Just a moment, just tell you a little bit about L'Hopital. It's kind of an interesting story. So L'Hopital himself, French guy, lived around 1700. Calculus was first developed in the mid 1600s. So think around 1650. And then publications were slowly coming out, right? Information obviously traveled a little bit slower back in those days. So L'Hopital was one of the first people, even though it's about 50 years after calculus was developed, he's one of the first people to learn of it. So L'Hopital himself came from a very wealthy family, served some time in the French military when he was younger. But by his mid-20s or so, he was retired from the military. And, you know, when you're very wealthy back in those days, there's not a whole lot to do with yourself. And so he decided to pursue one of his biggest passions, mathematics. So the way he went about that, he hired one of the Bernoulli brothers to come and teach him all the latest techniques in this brand new branch of math called calculus. So the Bernoullis are a whole story all themselves, but they were a father and 3 sons, and between the 4 of them made incredible advancements in mathematics and physics. And to make money, they would kind of hire out their services to go and tutor these very wealthy people, these very other wealthy men who wanted to learn about this as well. So it turns out L'Hopital did a lot of work in math himself, even up to this point, but he hires Johann Bernoulli. The Bernoullis were from Switzerland, so Johann Bernoulli travels to France, and he stays with L'Hopital. I imagine he stayed with him for several months, and, you know, lived there and tutored him. So kind of just where this is going with L'Hopital's rule, it turns out we call it L'Hopital's rule, but it wasn't L'Hopital who actually developed this rule. It was Johann Bernoulli. So part of the contract between L'Hopital and Bernoulli, when he was hired, L'Hopital said, okay, anything that you teach me is my property. So Bernoulli showed him the rule that he had come up with, that Johann Bernoulli had come up with. And a little while later, L'Hopital would write the first calculus textbook in the late 1600s, and it went across all of continental Europe. And so now calculus was much more accessible for people who wanted to learn about it. And in that calculus textbook, L'Hopital referred to the rule you're about to see by his own name. He called it L'Hopital's rule, even though he was not the one who actually developed it, but he did purchase it and it was under contract. Needless to say, Johann Bernoulli was not very happy with this, but he would lose the lawsuit because, as we said, L'Hopital did rightfully purchase that, and it was his property under contract. Okay. What's this rule all about? So we're going back to limits, but we're going to be able to perform some of these limits with our understanding of derivatives. So something like the limit as x approaches infinity for e to the 3x over 2x plus 1, not something we would have been able to do previously. We will be able to do it with L'Hopital's rule. Why? What's interesting about this? Like, why is this of any interest here? Why couldn't we have done it before? Well, if you think about plugging in infinity, and the truth is we really don't plug in infinity. Infinity is not a number, but sometimes it is helpful to think that way. Well, if we plug in infinity, we can see that e to the 3x is going to infinity, but so is 2x plus 1. And so we'd end up with infinity over infinity. And we do not have an answer to what that would equal. Turns out it depends on which part, the numerator or the denominator, is going to infinity faster. And so yes, they both go to infinity, but which one like runs away from the other one and becomes larger and larger much faster will determine that outcome. Turns out the outcome, the answer to infinity over infinity, it could be infinity. It could be 0. It could even be some number between 0 and infinity. Okay, we'll figure out what that is later. We'll also see this example eventually, the limit as x approaches 0 from the right for the square root of x times the natural log of x. Okay, interesting. What's going on there? Well, if we plug in 0, if you will, the square root of 0 is 0, but as the natural log of x, as x approaches 0 from the right, that would approach negative infinity. If you remember the graph of the natural log of x, it has a vertical asymptote at the y-axis. Now you might think for a second, well, hold on here, like 0 times negative infinity, that would have to equal 0, right? Well, slow down. So it turns out, or kind of hold on. Yes, we're saying 0, but the truth is the square root of x as x approaches 0 will never actually get to 0. It's just that the value of x approaches 0. So it's like really, really small positive numbers that are being square rooted. So we're getting very, very small positive numbers times very, very large negative numbers. These are getting closer to 0. This is getting closer to negative infinity. So we're not sure, is the answer 0? Is the answer infinity, or maybe negative infinity, or maybe it's some other number in between? Okay. Finally, we'll look at limits like this one. This one's pretty cool. The limit as x approaches 0 for the sine of x raised to the x. Ooh, excuse me. I was trying to hold back a sneeze there, but couldn't do it anymore. The sine of x raised to the x as x approaches 0. Right, if we plug in 0 here, well, the sine of 0 is 0, and it's being raised to the 0 power. Turns out we don't know the answer to that either. You know, this number for the sine x in the parentheses is getting smaller and smaller. The exponent is getting smaller and smaller. You might think, hey, like if you raise something to the 0 power, that should always equal 1, right? Well, yeah, unless that number you're raising is 0, because 0 raised to anything is 0. So you're like, well, is the answer 0 here? Is the answer 1? Maybe it's something between them. We're not sure. We're going to have to look at the details with L'Hopital's rule. Okay, so how do we go about this? First thing we need to do is define the indeterminate form. So we saw a few of those just now. Now we've got the full list. A limit is an indeterminate form if it results in any of these cases. So if looking at your limit, you get infinity over infinity, then we don't know the answer. It's not, we cannot determine the answer. It's indeterminate, right? Negative infinity over infinity, same situation. 0 over 0. Actually, we did see those things back in chapter 2, and typically we're able to figure them out even then, but we'll see what happens here. Okay, that's an indeterminate form. 0 times infinity, 0 times negative infinity. Infinity minus infinity, we don't have an answer to. Is the first infinity getting bigger faster, or is the second infinity getting bigger faster? Until we look at the details, until we apply L'Hopital's rule, we won't know which one of those would win. Infinity raised to the 0. Is it infinity, or is it equal to 1, right? 0 to the 0, just discussed, or 1 raised to the infinity. Would the answer be 1, Or would the answer be infinity because of the exponent? Or maybe something in between, right? Okay, so we recognize any of these we don't have an immediate answer to. So here's L'Hopital's rule. If a limit is an indeterminate form, then the limit for f of x over g of x as x approaches a is equal to the limit of f prime of x over g prime of x as x approaches a. So what we'll do with L'Hopital's rule, we'll need to think of what we're taking the limit of as being a ratio or a fraction, one function divided by another. If we take the derivatives of those, and notice the derivatives are separate, we just think of f of x sort of by itself, take the derivative there, g of x by itself, take its derivative. If we take the ratio of those derivatives with the same limit, then we can figure out what this original limit will be equal to. Why would that be? Why would we take the ratio of the derivatives? Well, if you think about the original limit, that's a ratio of y values, right? F of x over g of x, the y value for f over the y value for g. But maybe that comes out to something that we don't have an answer to. So what we'll do instead, if we have an indeterminate form, is look at the ratio of the rates of change, the ratio of the derivatives. How would that help? That would tell us which one wins, or what I say there, which infinity wins, right? It's like back in the case of infinity over infinity, which one of these, the numerator or the denominator, is going to infinity faster, right? So if I can know the rate of change of both of them, then I can tell which one is moving out faster than the other one. And that would determine what my final answer will be, or which one's the winner. I kind of like to think of the indeterminate forms as like a tug of war, right? So for infinity over infinity, the infinity on top is trying to pull the answer to infinity. The infinity in the denominator is trying to pull the answer to 0, right? Dividing by bigger numbers. Well, which one is pulling faster is going to determine the outcome. Even something like 0 times infinity, right? The 0 is pulling the answer to 0, the infinity is pulling the answer to infinity, and there's like this tug of war. Which one is headed there faster? Okay. So we're going to look at a whole bunch of examples. There's the rule again. It's kind of for our reference. One thing to keep in mind, you can only do L'Hopital's rule for indeterminate forms. Before applying the rule, you must check that the limit is indeterminate, that it is one of those 9 cases at the top. They might slip into the homework, some cases that are not indeterminate. So always check that first, right? Of course, they're going to be sneaky and give you some things where you shouldn't actually apply the rule, but do it in a way that we learned previously. Okay, we're going to do that. We've got 7 examples here, and that's going to be the rest of our conversation. So let me stop this video here. We'll pick it up in the next one with part A.